Okay, welcome to second part of the lecture for today. As announced previously, we want to look at transmission networks as kind of one of the balancing mechanisms of renewable feed-in. And I'm going to show you a couple of examples, what this balancing mechanism looks like, or what the effect of this balancing mechanism could be. And then we also need to run through a few definitions of how can we actually calculate the power flows in the network so that we can make sure that the network infrastructure is actually sufficient to serve this balancing need. So again, we're recording. And you also already know this model.energy platform is kind of small tool to let us optimize a simplified system with only wind, solar, and a constant demand, and then some battery and hydrogen storage as balancing mechanisms. But we can actually also, even though the transmission networks cannot be modeled explicitly, we can also roughly approximate what the potential benefit of kind of aggregating renewable resources over larger areas could be. So as a first start, I picked kind of one central point in Germany and let this model run that you all know, but we need a certain reference point. So here we're optimizing the cost of this 100% renewable electricity system for this one site. In fact, it's kind of 130 by 30 kilometer grid from the Area 5 dataset that you know. And we're ending up at a cost of 91.2 euros per megawatt hour. So that's our reference point. And I also, oops, that's not what I wanted. I also ran this for Germany, for the whole of Germany, where the whole renewable resource, the profiles are smoothed, which is basically the same as a perfect interconnection between each of the raster cells in the model within Germany. So maybe a quick show of hands / type in the chat question. Who thinks it's more than 10% or 20%? Who thinks it's more than 10% cost reduction? Okay, nope. You all think it's lower than that. Who thinks it's lower than 10% cost reduction? So if I now move from the single site to aggregating over all of Germany, so basically perfect interconnection and perfect smoothing of the wind feed-in across Germany, how much lower would the average cost be? So we had 91 euros per megawatt hour in the single site case, and how much lower will be the cost for this case? Assuming that the point we looked at is fairly average capacity factor site. Who thinks it's more than 10%? Okay. Who thinks it's less than 10%? Okay. So it's actually much more than 10%, going down to 71 euros per megawatt hour. So that's more than 20%, actually. And if we now go to a third case, where I drew up coarsely the shape of Europe, and let's just assume roughly that kind of if we average over all of Europe, that's roughly the same as same capacity factor as Göttingen, so the central point in Germany and Germany overall. Who thinks that the further cost reduction is higher than 10%? So from the Germany case to the Europe case. Who thinks it's less? Okay. So it's even more. So it's another 30 euros per megawatt hour cost reduction. Of course, there's a catch. It's a simple model. It doesn't factor in any cost of building the transmission grid. And maybe I'm also wrong in assuming that kind of the average of Europe is has the average capacity factor profile as Germany. But in general, I think the notion here is correct that you get the biggest benefit of aggregation, especially for wind-dominated system, by aggregating over larger areas. So you get a nice smoothing effect by aggregating from east to west for solar, because that smoothens out, because the sun rises in kind of east, and then you have later sunset in the far west. If you have good connection east to west, then you have smoothed solar feed-in profile throughout the day. It's less spiky. You also average out cloud coverage, things like that. And also for wind, the wind is determined by the weather systems, roughly something like 600, 700 kilometers wide. So if you integrate over an area that is bigger than 600, 700 kilometers, which is the case for Europe, then you get the case, you really can benefit from the fact that it's windy somewhere under the assumption of perfect interconnection. And you can see that in kind of these time series we looked at in the first lecture. Here is for a time series for the case of Berlin, quite spiky wind production. If you aggregate over Germany, you can't see much here, but it's in the statistical quantities, it's a bit smoother. And then if you average over all of Europe, you get an even smoother profile where especially you don't get the spikiness and you fill in the blanks here. You can also see that in the duration curves. Here, the lighter shade for all of Europe, kind of more widely distributed over the year, and also in the residual load duration curves. So these are the residual load duration curves we talked about in the last lecture, where red is your residual load curve for Berlin, Germany, yellow for Germany, and bluish for all of Europe. And why did I say you can see that also in the residual load duration curve? Maybe let's spend 1 or 2 minutes on why I can see that in the load duration curve. Well, I can, especially in the ends here, I can see that if we aggregate over Europe, the load duration curve is much smoother. So the differences between the highest excess and the highest shortage, so this would be the shortage, this would be the highest excess, are much smaller than if I look at more isolated regions. So this means we have not only storage, demand side management, balancing in time as one option to balance renewables, but also balancing renewables in space through transmission networks or general energy transport. The big caveat in these examples I showed at the beginning is that we don't have perfect transmission. We have extensive transmission, highly interconnected across all of Europe, but there are also increasing bottlenecks. We can't always assume that we can actually transport the power, and then there are also physical laws that determine the power flow in the network. It's not the case that we can simply route power through the network, but it has to follow just the physical laws, and these are, we sometimes say, passive because we have limited control over it. There are power electric devices that can help you control the power flow in the network, but generally that is not the case. So you have limited controls, and your power flows must meet these Kirchhoff laws, so-called Kirchhoff laws, and you must also respect just the thermal limits, so how much current can go through the individual lines. But in principle, the whole network is interconnected from the south of Spain to the northern Norway. So what we have in each of the nodes of the transmission network is that we potentially have some withdrawal from the grid or some injection into the grid. We'll call these power imbalances from now on at different points T and at the different locations I. And for every point in time, first of all, we have to balance the power injection overall, but it doesn't need to be balanced at each node. It just needs to be balanced at at each node considering the incoming and outgoing flows. So why could there be overloading? Well, you have not only the renewables, but also the load that is spatially distributed differently. We have higher wind speeds in the North Sea, good solar resource in southern Europe. You have the load centers like Northern Westphalia, Paris, London, and so on, that have higher industrial concentration, higher population, and therefore higher electricity demand. And especially as you go to a more renewable system, you really need to align, for economic reasons, these sites of production, which today may be some power plants, which may be decently close to the demand centers, to the consumption sites. So if you have not the right amount of transmission capacity in the network, and you need to avoid the overloading, then you need to curtail the renewables or even ramp up some fossil power plants. So this curtailment, so not using electricity from renewables that could be available in principle, has increased over the past years. Probably not so much news for you. I couldn't find an English version for that, but it shows you just in billion kilowatt hours. So that's terawatt hours. I hope, yeah, that's terawatt hours. The progression of curtailment over the years, and also broken down into different categories. And most of the curtailment is done for offshore wind and onshore wind, and only very little is done for PV. So it's more than 90% it's onshore and offshore wind. The curtailment mostly happens at the high voltage transmission level. It's about 75%. This is where the bottlenecks are currently. And what this number 10 terawatt hours means is maybe something like 2 to 3% of German electricity consumption. That's renewable electricity that is generated that cannot be used for operational reasons in the transmission grid. That mean that 2%, 3% of the electricity consumption we cannot cover by the renewables. And the increasing trend over the last years I already mentioned. So that seems to indicate that it's quite important to understand the bottlenecks of the transmission networks and how to calculate the power flows in the first place. So let's break that down to a little bit more simple problem. Maybe some of you have seen this in some other courses from our department. Assume we've been given this PIT, I dropped the time index here, of power injections. Positive would mean injection into the power, and negative values would be net consumption at the node. So here, this node would be consuming, these two nodes would be producing net. So how do power flows distribute in the network? And the naive version would be you would maybe say something like this. Say, okay, I have 50, I need to bring it here, so I send 50 here. And well, this is also completely wrong. But anyway, I send 50 here, I produce another 50 and send 100 to this node. Probably what many of you would say if you don't know about power flow. Yeah, I don't know if you do know this already, but I mean, from a naive point of view, if you don't know anything about it, this could be reasonable. This is not the case, of course. Otherwise, I wouldn't have put it this prominently here. And to understand that, we need to just run through a few definitions. I'm sorry for that. And we need to both include some equations from power flow and also understand some of the vocabulary to work with graphs. So graphs is just a mathematical concept to describe the relations between these nodes and so-called edges, connections between nodes. So I'll be fairly quickly with that. If anything is unclear, then please stop me. So this is really just about definitions so that we can work with them later. So you have a network, it's just a graph of vertices or nodes joined by edges. The vertices in this case would be the nodes 1 to 6, and the edges you can just describe as connections between nodes. You have the order and the size. They just tell you about the number of vertices, and the edges in the network, so just some statistical quantity. If you take the European network we looked at before, you have something like 5,400 vertices, 6,500 edges, and each of these edges, they can have, and also the nodes, they can have some additional attributes. For example, what the capacity is, what the electrotechnical parameters is, what their length is, what their voltage is, or what their coordinates are. And this is the foundation for calculating the power flows in the end. For calculating the power flows, we need to find out what the relations between the vertices and the edges of a graph are, and we need to work with a few matrices, so-called adjacency matrix, for example, that just tells us which edges or which vertices are adjacent to another vertex. So I and j would be nodes in the graph, and you would have a value of 1 if so there's a connection from 1 to 2. So on the 1 to 2 as well as 2 to 1, you have a value of 1 because we have no sense of direction here. So it's kind of typically a symmetric matrix for any graph that is not directed. This would be a matrix, kind of number of nodes by number of nodes. The degree of a matrix would tell you how many edges are connected to a node. So for example, for this node 3, we have 3 edges connected. So the degree of this vertex, the degree of this vertex is 3. The degree of the node 5 would be 1 because it's only one connection. Of 6 would be 2 because there's only 2 connections. If you want to find out generally how densely connected your network is, then you might look at something like the average degree of the network. So on average, how many other nodes a node is connected to. So in this case, it would be 2.3. We have a little over 2 connections on average. Okay, another matrix that plays a role here, and that is actually the more important one for calculating the power flows later on, is that we have, say we have a directed graph, so some orientation from 1 to 2, rather than just a connection between 1 and 2. We formulate this incidence matrix that tells us for every line where it starts and where it ends, at what node it starts and where it ends, namely a value of 1, if the edge L starts at node I, and -1 if it ends there. So that if we build power balances of each of the individual nodes, which is one important equation, Kirchhoff's current law, as we'll see in a moment, that the kind of each node has to maintain the power balance of the net injection into the network and the incoming and outcoming flows. This definition will be quite valuable. So in this graph here, we have a connection from 1 to 2. So we have a value of 1 for the first row, which represents vertex 1, and -1 at the receiving end. So that would be node 2. And then if we pick this edge 3 or connection 3 from 2 to 4, we have a 1 at row 2 and a -1 at row 4. Goes from 2 to 4. So the sums always end up summing up to 0 because you have each edge has a starting point and end point, and that kind of preserves that whatever power you send in through one end, it is received at the receiving end of the line. So that we really build this connection and an energy or connection of energy balances for each of the different nodes. One other definition that we're going to need in a moment is the concept of cycles in a graph. So a cycle is just basically what the name says, some path along edges that return to the starting node. So if you take this graph here, there's one cycle in this network. You go from 2 to 4, from 4 to 3, and from 3 to 2, while you go in the opposite direction for some of these nodes. And you would write this combination of edges as 0 if the edge is not part of the cycle, 1 if you go along the direction of the edge, and -1 if you need to go the opposite direction. And that just gives you a definition of a cycle in the network. And the Kirchhoff's voltage law that we'll see in a moment that has the requirement that the so-called voltage angles across a network have to sum up to 0 for every cycle in the network. So that just we'll derive that in a moment, but that's a kind of this the other Kirchhoff law that we need to take care of, and for that we need to know what the cycles are, and we can formulate that so-called cycle matrix where you just have a column for each of the cycles, and for each of the and you have for each of the cycles the lines that play a role in them, either in a positive or negative direction. Okay, so I already mentioned Kirchhoff current and voltage law. For the current law, we mainly use the incidence matrix, and it's just used to enforce energy conservation at each of the vertex. It looks complicated, but it's just you take the power imbalance, and the power imbalance has to equal the sum of incoming minus outgoing flows. So if Pi is positive, you have some injection into the network, and that should have the same orientation in this equation as some import from some other region. And for that, we just use we sum up over all the lines that are connected to this particular node I and add up the flows. So remember, there's this -1 value here for every node that is at the receiving end. So in this example here, it's relatively straightforward to calculate. You would all do this energy balance, I think, intuitively. You have some production here. You send 12 through here, so that's a 1 power flow calculated. You have consumption of 2 here, so you have 10 left. So you need to send 7 through here to supply this demand, and 3 through here to supply the demand. And that is already a unique solution. The unique solution, or the fact that we could find a unique solution here for the given injection patterns, has to do with the fact that we don't have any cycles in this network. So if we don't have any cycles, Kirchhoff's current law is actually sufficient. We don't need to take care of any cycles because Kirchhoff's voltage law says the voltage angles around each cycle in the network have to sum up to 0. So if we don't have any cycles, then we don't need to worry about it. For Kirchhoff's voltage law, we need to work with the original AC power flow equations. And it looks quite complicated, but I just added them here for completeness. So in principle, the AC, so alternating current power flows, is a non-linear equation. Different ways to express them, but you can express them in voltage polar coordinates. So voltage polar coordinates, because you get for the quantity of voltage, electrotechnical quantity, you get a voltage magnitude. So these are the capital V's at the different nodes. It's a node attribute, as well as the voltage angles. So you have magnitude and angles. So that's polar coordinates, where you have theta I and theta j as the voltage angles of the network. And then you have some electrotechnical quantities like the resistance and the reactance, just some attributes of the lines. These are fixed values depending on what materials you use and stuff like that. So in energy modeling, we typically linearize everything, and that has to do with the fact that linear models are much, much easier to calculate, to solve, especially bigger problems. It's the status quo, the gold standard in energy system modeling for building renewable electricity energy networks. So we can't work with these equations directly. But there are a couple of assumptions that we make and that are valid to some extent, or at least reasonable approximations for linearizing the power flows. And one thing is we say that the reactive power flows are negligible compared to the real power flows. If you don't know what the difference is, it's too complicated to explain in 1 minute. But it's basically different physical quantities of flow, that the voltage magnitudes are close to one, so that you don't have. So if your your network runs nominally on 380 kilovolts, you assume that it runs on 380 kilovolts and not 379, which in some cases of the network it might actually is. And then your quantities here, that the resistances are small compared to the reactances. So you have dominance of one of the electrical parameters. And then you do small angle approximation that you maybe know from other math courses, for example, or other engineering courses, that your sine of the angle differences is approximately the angle difference itself. And what you then get out of that is just this simple linear equation that your flow in the network is related to the voltage angle differences by the reactance, the physical quantity, or the attribute of the line itself. So if you want to understand step by step how this comes to be, you can go through these 4 slides step by step, but they basically break down, they apply each of these approximations, and you can see how step by step the equations becomes a little bit simpler. It's not super complicated, but also not worth me going through it, I guess. But what do we make of that? So we now have a linear relation between the voltage angle differences. So something where we know Kirchhoff's voltage law says the sum across all the voltage angle differences in every cycle in the network has to sum up to 0. So we know how Kirchhoff's voltage law relates to these voltage angles, and we can relate the voltage angle differences to the flows in the network through the reactance. So that helps us to formulate a linear equation for Kirchhoff's voltage law. So this is just kind of the complicated version of the voltage angle differences, again using the incidence matrix. So this just builds the voltage angle differences based on the connectivity of the nodes and lines across all the cycles in the network. So for each cycle, we use our cycle matrix, which just tells us which is an indicator matrix, which of the cycles are part of the cycle, which lines are part of the cycle and in what orientation. This is just what I said earlier. The sum of voltage angle differences across each cycle in the network has to sum up to 0. So this is one equation. And this part of the equation here, we can substitute with this. And I'll show you how to do that. So if earlier we derived this equation here, this part, and if we use the incidence matrix for that again, we can express it like this, that 1 over XL times this sum of voltage angle differences. So that's something we know from here. So if we just kind of reformulate that, so FL times XL, we have this expression here, and substitute that into this equation here, we get a nice equation that looks a little bit more manageable. namely that XL times FL across all the cycles in the network for all the across all the lines in a cycle for each cycle gives us our Kirchhoff voltage law. And these are L minus n plus 1 equations. And in general, that is then sufficient, even if your network has cycles, to uniquely determine the flows in the network in combination with the power balances with the Kirchhoff current law. So what you have here is really just one unknown that you would like to calculate in an equation system, and these two values here, the XL electrotechnical parameters that you know up front, and the CLC is just the connection, the topology of the graph that you also know up front. So in total, we now have kind of n minus 1 equations for the flows and L minus n plus 1 equations from Kirchhoff's voltage law. So we have L independent linear equations for L variables. For every line, we have one thing that we want to calculate, and we can solve that. No problem about that. And this is just really, if you have the power imbalances given, you can really just solve it as a linear equation system and get the power flows out of that. So I brought one illustrative example here where I took a slightly aggregated version of the European grid. And this for 100% renewable electricity simulation for one particular hour. So we're just looking at 1 hour here. And we have been given this graph here. So what comes with this is basically the incidence matrix, the cycle matrix. So that information we just get from this topology, and also the impedances, the XLs of the lines we also have given. And we are also given the power imbalances. So everything that is blue is where our PI is positive, we have net injection, and everything that is in red, we have net consumption in this network. So now we have the topology, so incidence matrix and cycle matrix, the reactances, so the XLs, and the power imbalances. So looking back at these equations, we actually have everything given with the exception of the flows that we want to calculate. So we can calculate the flows, and what we can get out of that, so I didn't add legend here, but yellow means high loading, blue means low loading. What we get here is we get an image of where the flows are high, where the flows are low, and also in principle where if you have, for example, a model that doesn't account for the grid, and you put the decisions into a grid model that considers the transmission bottlenecks, you could, for example, check here whether there would be any outages, not outages, but overloadings in lines, where if you executed that plan, you maybe want to check, well, is this actually technically feasible, or would that incur some overloadings, for example, here in these lines in Poland, for example. So yeah, where does this leave us? So one thing that we kind of glossed over was the PI. Where do we get the PI from? And that will be most of our focus for the upcoming weeks, where we use methods of optimization and maybe try to understand a little bit how electricity markets work. We'll introduce you to some of the fundamentals there, where we will discuss how it is decided which power plants operate and which and in principle also where electricity is consumed, from which we can then derive these imbalances PI and calculate the power flows. In many cases, you would actually put both of these things into a single model where it endogenously determines the power imbalances and at the same time calculates the power flows and even adjusts the dispatch decisions based on knowledge of where some solutions might not be feasible because they would cause overloads in the network. So you build a model which really ensures that you have the technical feasibility of the power flows and then try to find the optimal way to calculate the PI. And fundamentally, there's a difference between today's system, where we know where most of the demand is, and most of the unknown variables are just the dispatch of the power plants and maybe some of the hydroelectricity storage. And in future system, this can just become much, much more complicated. We need modeling to understand that, how this stronger interplay of generation, variable generation, storage technologies, transmission limits and potentially transmission expansion, as well as flexible demands and coupling to other sectors like heat pumps, electric vehicles, play a role there. So this is going to be the focus of the next few weeks, how electricity markets work and how optimization problems work. And before that, so that's actually already going to be next week. But I don't want to bore you only with lectures, but also with some new Python packages. And next week, we're going to look at PyChats, which is a tool to calculate these catchment areas of the hydroelectricity plants that we discussed in the first lecture today, and then Network X, which is a Python package that just helps you work with networks and graphs. That was fairly quick, so I'll leave it at that for today. If you have any questions, I'll stick around for a few more minutes. Otherwise, I'll just conclude for today.